Hi guys, welcome to this video. So in this video we'll be looking at atomic structure. So atomic structure is a very complex topic, okay? And if you do not have the proper guidance, you find it hard to answer questions under atomic structure. Okay, for that reason, I'm going to focus on the most important things that will make sure that you can answer any question that can come under atomic structure. Okay, so to begin our discussion, well, we're just going to simply go over some of the important formulas that we use under atomic structure. Okay, so the first formula that we are going to look at is the formula that relates the speed of light, the frequency, and the wavelength. Okay, so we are going to say the speed of light indicated by c is equals to frequency, okay, multiplied by wavelength. So this guy here, this symbol is called lambda. Okay, and under atomic structure it will be representing wavelength. Okay, so wavelength should always be in what? Meters when you're solving questions, but it can be given in any other subunits of length. Okay, but when you're solving question, make sure you convert this wavelength to meters. And then this one here that looks like a V is frequency. Okay, so frequency is measured in hertz or seconds to the power 1, or you can say 1 per second. So whenever you see these units, or these units, just know that they are talking about what? Frequency. Okay, and then this C here indicates the speed of light. Okay, it indicates the speed of light. So the speed of light has a constant value. So we'll be using C is equals to 3.0 times 10 to the power 8 meters per second. Okay, so this here is the speed of light. So that is the first formula that we are going to be using under what? Atomic structure. Okay, so the other formula is the formula that involves calculating energy. Okay, calculating energy of these different particles or atoms or whatever. So that formula states that, okay, the energy is equals to H multiplied by V. So this H here is what we call as Planck's constant. Okay, Planck's constant, and it has a value of H is equals to 3.626 times 10 to the power minus 3 to the power minus 34. Okay, this one here we already said it's the frequency. Okay, it's the frequency. Then this one here will be the what? The energy. Okay, and then the other formula that you can use to calculate the energy is what we call as the Einstein's formula. So that formula states that the energy is actually equals to mc squared. Okay, and then this C here we are saying is the speed of light. Okay, but in a more general form, we can put any speed there. Okay, so as long as you have the mass at which something, as long as you have the mass of something and the speed at which that thing is moving, then we can calculate its energy according to the Einstein's formula. Okay, so from this formula, and the one that I gave for speed of light, where we said this one, okay, from these three formulas we can come up with another formula that we can use to calculate what? Energy. Okay, so from this first formula here, I'm going to make this frequency the subject of a formula. So if we make the frequency the subject of a formula, we're going to have speed of light divided by wavelength. Okay, and then I can come to this formula. I'll say energy is equals to H and then the frequency. Okay, so H, this frequency here is the same as this one. So I'm multiplying H with the C divided by lambda. So sometimes you can use this formula here to find the energy. Okay, you cannot be given the frequency. You can just be given the wavelength. Okay, and we know that this Planck's constant is a constant, which is this one. Even the speed of light is a constant. Okay, so just given the wavelength of something, we can be able to calculate the what? The energy. Because this one is a constant, we know its value. Even this one is a constant, we know its value. Okay, and then from this formula, okay, we see that energy here, okay, this energy here is equals to mc squared, and then this energy here is equals to hc divided by lambda, or wavelength. So we can come up with an equation that will help us find the mass, okay, of a particle that is moving at a certain speed and has a certain wavelength. Okay, so that will be the application there. So let's come up with that formula. Okay, so we're saying energy is equals to this, so write mc squared is equals to, okay, again this same energy is equals to this, so we can equate hc divided by lambda there. Okay, then we make m the subject of the formula, so we divide both sides by c squared. So what we are going to get is hc over lambda divided by c squared. So dividing by c squared is the same as multiplying by 1 over what? C squared, because this will change to multiply, okay, and then this c squared we can write it as 1 over what? C squared, like this. Okay, so you see that one of the c's goes, and then this c goes, I mean, and then one of the c's from here goes. So it means our mass will just be calculating as Planck's constant divided by lambda, which is the wavelength, multiplied by c. Okay, so whenever we want to calculate the mass, we'll be using what? This formula. Okay, so those are some of the formulas that we're going to be using here. Okay, so another important thing that we can talk about under atomic structure are the energy transitions. Okay, so from your grade 12, we were told that the structure of an atom is something like this. You have the nucleus there, okay, which has protons and neutrons, and then around this nucleus, okay, you have these energy levels like this. Okay, so this is an energy level, and then you have another energy level like this. Okay, just like that. So these energy levels can go all the way up to infinity. Okay, so we'll say that this is energy level number 1, so we'll call it N1. Okay, and then this one here will be N2, this one here will be N3, this one here will be what? N4. Okay, so from those energy levels that we have, okay, we can see that this is the energy level number 1, energy level number 2, energy level number 3, energy level number 4. Okay, so in these energy levels we have what? Electrons. So these electrons here, they can move from one energy level to another. So if, for example, I have an electron there, okay, this electron here in this energy level, it can gain energy and then it can move and go to the energy level number 4, so it will be somewhere there. Okay, so what has happened to this electron? It has gained energy and then it has moved to a higher what? Energy level. Okay, so this process of moving from one energy level to another, okay, requires energy. Okay, so if you are moving from a lower energy level to a higher energy level, it means this electron here, okay, this electron here would have gained energy and then it goes to the higher energy level. Okay, but even the reverse scenario can happen, where you have an electron in a higher energy level, okay, and then it loses energy. So what happens? It drops back to a lower energy level. Maybe it comes there. Okay, so this process where the electron was in a higher energy level, okay, and then it drops back to the energy level which is lower, okay, it will say that here the electron has what? Lost energy. Okay, and then there we said it has what? Gained. So here it was in a lower one and then it gained, it went to a higher one. Here it is in the higher one here and then it loses energy, okay, it comes to a what? To a lower one. Okay, so these energy transitions, they can be calculated. Okay, so we are going to say the change in energy, okay, from a particular energy level, okay, to another energy level will be given by this formula. So we are going to say minus 2.178 times 10 to the power minus 18. Okay, and then in brackets we are going to write 1 over, okay, the final energy level, and then you square it, and then you say minus 1 over the initial energy level, and then you square it like this. So this is the formula that we are going to be using when finding the energy, okay, of these transitions from a higher one to a lower one, or from a lower one to a what? To the higher one. All right, and then another formula that we can discuss here, okay, is what we call as the the Rayberg's equation. Okay, so the Rayberg's equation is special because it directly relates, or connects the wavelength to the energy levels. So what does the Rayberg's equation state? Okay, it states that 1 divided by the wavelength is equals to 1.096 times 10 to the power 7. Okay, and then in the brackets we have this same thing here, so it will be 1 over the final energy level squared minus 1 over the initial energy level squared. So these are basically the formulas that we are going to be using under what? Atomic structure. Okay, and then the next thing to talk about, okay, is what we call the series. So we have about 5 series that you need to know. So these series, okay, just simply tell us the final energy level, okay, that an electron will move to, and they also tell us the type of electromagnetic wave that transition of the electron is going to make. Okay, so remember I had drawn this. Okay, if I can bring back this image, I had drawn this. I said the electrons can move from there to the lower energy level. Okay, so we have what we call as the transition series. Okay, so this series, 1, they indicate the final energy level. Okay, and then 2, they tell us the type of electromagnetic radiation. Okay, so let's erase this part here. Okay, let's erase this part. Okay, so we have about 5 of them. Okay, so the first one is what we call as the Lyman series. Okay, and then we have the Balmer series, and then we have the Passion. Okay, and then we have the bracket. Okay, and then the last one is what we call as the P-Fund series. Okay, so I said this series tell us what? The final energy level that an electron will move to. So whenever you hear the Lyman series, just know that the final energy level is 1. Okay, so N final will be 1. When you talk about the Balmer, N final will always be 2. When you talk about the Passion, N final will always be what? 3. When you talk about the bracket, N final will always be 4. Okay, so it can come from whatever it's coming from. Okay, but the final one will just be what? Will just be 4. And then if we're talking about the P fund, the N final will always be what? 5. Okay, so if I could put this into a picture, it's something like, okay, let me draw the energy levels as just straight lines. Okay, like this. Okay, so let's label them as this one here is N1, this one is N2, this one is N3, this one is N4, and then this one is N5. Okay, so an electron can come from whatever energy level, okay, but as long as its final destination is the energy level number 1, okay, we are going to be calling those as the Lyman series. Okay, so the Lyman series has the final energy level as what? 1. Okay, so it can come from whatever energy level it's coming from, but the final one should be what? 1. So these Lyman series, okay, they exhibit what type of radiation? Okay, they exhibit ultraviolet radiation. Okay, they exhibit ultraviolet radiation, and then you can have another transition, okay, where the final one is energy level number 2. Okay, so it can come from wherever it's coming from, as long as the final one is this energy level number 2. Okay, we're going to call that as the what? The Balmer series. Okay, so the Balmer series, what is their electromagnetic radiation? It's visible light. Okay, it's visible light. Okay, and then if you are talking about the Passion, okay, it means the final energy level, it can come from wherever it's coming from, but the final one should be what? Energy level number 3. That's what we mean. Okay, so the transition can happen from energy level number 7. As long as the final one is 3, we are going to say that is the what? The Passion what? Series. Okay, so this one here, it's related to infrared radiation. Okay, so from this point where you have n3 going upwards here, okay, the radiation that you are going to be involved in will always be the infrared. So it means even if the final one is 4, you are still going to have infrared. Okay, if the final one is 5, you're still going to have infrared like that. Okay, so if the transition happens from whatever energy level, okay, but the final one is 4, we'll call that as the what? The bracket. Okay, we'll call it as the bracket what? Series. And then if a transition happens from whatever energy level and the final one is 5 like this, okay, we're going to call that transition as the what? The P fund. Okay, so just by the final energy level that you've been given in the question, you can tell 1, the series, okay, 2, the type of electromagnetic radiation that is involved with that transition. Okay, so what I've told you here are the basics that we are going to be using, okay, as we solve questions. All the questions that are involving this atomic structure thing are going to be centered on this part. All right, so now let's solve some example sample problems. Okay, so let's look at the first one. So the first one here, they're saying what is the wavelength in nanometers of an electromagnetic wave whose frequency is 3.64 times 10 to the power 17. Okay, so here we use the wavelength, the wave equation I mean. Okay, so we know that the speed of light is just equals to the frequency multiplied by the wavelength. Okay, so we want to find this wavelength, so we can make it the subject, so it will just be speed of light divided by the what? The frequency. Okay, so we know the value of the speed of light is just 3.0 times 10 to the power 8. Then we're going to divide this by the frequency, which is 3.64 multiplied by 10 to the power what? 17. Okay, so here you should be confirming as well with your own calculators. Okay, so when I divide this, okay, what am I getting? So my calculator is giving me 8.24 multiplied by 10 to the power minus 10 meters. Okay, so this is the wavelength here, but this is not the final answer, because remember in the question they are saying nanometers, so we have to change these meters into what? Nanometers. Okay, so we can use a conversion factor there. So we know that 1 meter is equals to how many nanometers? Okay, it's equals to 10 to the power 9 nanometers. Okay, so what about if we have these meters? So we're going to say 8.24 times 10 to the power minus 10. Okay, if these are meters, how many nanometers are we going to have there? Okay, so we can just represent that as x. So from there we'll just cross multiply. So cross multiply, x will be equals to the multiplication of these two. Okay, so here I have 8.24 multiplied by, this is 10 and this is 10. Okay, so they have the same base, so I can just add their powers. So minus 10 plus 9, I'm just going to get 10 to the power minus 1. Okay, so 8.24 multiplied by 10 to the power minus 1 is the same as x is equals to 8.24 divided by 10. So this will give me x is equals to, okay, 0.824, and these are what? Nanometers. Alright, so that's how we can solve our first problem here. So they can ask you to solve to find any of these, okay, provided they give you the two of them. So they can ask you to find here we are finding the wavelength. Okay, some questions they can ask you to find the frequency. Oh, that's the wavelength. They can ask you to find this frequency here. So it means they will just give you the what? The wavelength. And then we know that this speed of light is always a constant. So it is just 3.0 times 10 to the power what? 3. Right, so that's how we can solve that problem. Let's look at the next problem. Okay, so the next problem they're saying a particle moving with a wavelength. Okay, so the wavelength is 6.6 times 10 to the power minus 4 centimeters. Okay, a particle having the wavelength of this is moving with a velocity of, okay, so we're going to say the velocity here is equals to 1.0 times 10 to the power 6 centimeter, okay, per second. So this centimeter per second is the same as centimeter, and then the right centimeter, centimeter, and then the right second to the power minus 1. So this here is the same as what I've written there. Okay, so the question now is find the mass in grams of this particle. Okay, so how are we going to find the mass? We just have the wavelength and the what? The speed. So remember the equation that I derived when I was telling you about the formulas that we are going to be using. Okay, we said energy according to Einstein's formula was mc squared if you're dealing with the speed of light. Okay, but if you're just dealing with a general speed, you can just write v squared. Okay, and then the other formula that we used to calculate energy, okay, we said it was energy is equals to hc and then divided by lambda. So we equated this and this to derive the formula for the mass. Okay, so we said mv squared is going to be equals to, so here now we are not using the speed of light, we're just using any other speed. So where there's c there, you can just put any other speed like v. Okay, so it means I'll have hv and then lambda. Okay, and then from here we said we divide both sides by this speed, so the mass was equals to, okay, the mass was just equals to h divided by the speed multiplied by lambda. Okay, so then to differentiate this speed here that I'm indicating by v and that symbol for the frequency like this, so this one here is not the v. Okay, it's you can call it as mu. Okay, something like that. Okay, all right, so learn to differentiate the two. So it means that the mass, we can find it by this equation. Okay, and then we said h was Planck's constant, okay, which is 6.626 times 10 to the power minus 34. Okay, and then the speed has been given as this one, the lambda has been given as this one, but we have to change this speed and wavelength to the standard units. Okay, so we said if your wavelength is not given in meters, you have to change it to meters. Okay, so we have to change this centimeters to what? To meters. So we just use the metric system. We're just going to write 6.6 times 10 to the power 4, and then where there's centi here, I'll put the value for centi. So centi is 10 to the power minus 2, and then I have meters. So where there was centi here, I've put what? 10 to the power minus 2. Okay, so if you are confused here, watch the video on converting what? Units. Just search on my YouTube channel, Twitter converting units. You're going to find it. Okay, so it means here I have 6.6 times 10, and then these are the same bases. Okay, so we can add the powers. We're just going to have 6. So this is meters. So this is my wavelength, and then this speed here, I have to change it into what? Meters per second, because here it's in centimeters per what? Second. Okay, so I have to change it to meters per second. So how do I do that? Okay, I use the dimensional analysis. So this is 1.0 times 10 to the power 6. So I'll write centimeters here, and then I'm going to divide by seconds. Then I'm going to say multiplied by, write a line here. Okay, so the lines that I want to disappear from this equation are the units, I mean, are the centimeters. So I'll put centimeter down here. So how many centimeters make up a meter? Okay, how many centimeters make up a meter? It will just be what? To just be 100. Okay, and then here I have 1 meter. Okay, so when you multiply this, what you're going to get is 1.0 times 10 to the power 6, not power 6, okay, 10 to the power 4, and then meters per second. All right, so we've converted our speed, so we can write it here, meters per second. Okay, so what is left now is just to use that formula for calculating the mass. Okay, just plug in the Planck's constant, our wavelength, and our speed. So we're going to say mass is equals to, okay, the formula was Planck's constant divided by lambda multiplied by this velocity. So the Planck's constant is 6.6, okay, 26 times 10 to the power minus 34 divided by, okay, we have the lambda here, so 6.6 times 10 to the power minus 6 multiplied by, okay, the velocity, which is just 1.0 times 10 to the power 4. So this is what we have. Okay, so we can punch this into our calculator. So to avoid confusions here, you may want to group all the numbers that have 10 to the power somethings together, and then those that do not have together as well. So I'm going to write this number, okay, as 6.626, okay, and then I'll say multiplied by 10 to the power minus 34. And then I'm going to say this here divided by, here I'm going to write 6.6 multiplied by the 1 from here, and then I'll put 10 to the power minus 6 times 10 to the power 4 there. Okay, so this makes it easy because we can deal with this alone, okay, because they have the same bases. So from this we have to add the powers first of all. Okay, so we're going to get something like this. Okay, so we're going to say mass is equals to, so here we can divide this. Okay, so this will be 6.626 divided by 6.6 multiplied by, here these ones here are multiplying, so we can add their power. So minus 6 plus 4, it will be 10 to the power 2, okay, to the power minus 2 I mean, and then we have this and 10 to the power minus 2. Since they are dividing, we can subtract their power, so it will be like 10 minus 34 minus 2, so that would be like 10 to the power minus 32. So that's what I'll put here. Okay, and then from here I'll just multiply this now onto my calculator. Okay, so when I multiply that, I am getting approximately, okay, I'm getting approximately 1.00 times 10 to the power minus 32. So I'm getting okay, let me punch this again. So I have 6.626 divided by 6.6. So I have 1.00393939 times 10 to the power minus 32. Okay, so I can just round off that to 3 significant figures. Okay, so it means the answer will just be mass is equals to 1.00 times 10 to the power minus 32. And remember, this mass, we said it should be and remember the mass from this formula, okay, this formula here, we said it will always be in what? Kgs. So this is the mass in kgs, okay, and then now you want to change this mass into grams, because here in the question they said we should change the mass into what? The grams there. So we can change that kg to gram. Okay, so I'll write mass is equals to 1.00 times 10 to the power minus 32 kgs. Okay, so this will be the same as, okay, this will be the same as 1.00 times 10 to the power minus 32, and then where there's kilo here, because this is kilogram, right, I'll put its value. Okay, so kilo is the same as 10 to the power 3, so I'll write 10 to the power 3 and then I leave the grams. So this would be 1.00 times 10 to the power minus 2 multiplied by, okay, here it will be, in fact we can add those, so I can say, because the bases here are the same, this would be minus 32 plus 3 grams. So it means I have 1.00 times 10. Okay, what is 32 minus 32 plus 3? Okay, so that would be minus 29. Okay, so that would be minus 29 grams. So it means the mass of that particle in grams is just 1.00 times 10 to the power minus what? 29. 3 is on transitions. Okay, so they are saying calculate the frequency, the energy, the wavelength in nanometers of a spectral of line of hydrogen. Okay, for the transition n is equals to 6 to n is equals to 3. And then they're saying, would you expect to see this light corresponding to this line spectra? And then C, explain your answer. Okay, so we want to calculate the frequency, the energy, and the what? Wavelength. So we can start from the wavelength. Okay, so we'll use Reybak's equation. So we're going to say 1 over wavelength is equals to 1.096 times 10 to the power 7, and then we have 1 over n final squared minus 1 over n initial squared. So here they are saying the transition is happening from n6 to n3. Okay, so it means the initial is 6 and the final is what? 3. So let's calculate this. So it will be 1 over lambda, which is the wavelength, 1.096 times 10 to the power 7, then 1 over the final is 3 squared minus 1 over 9 squared. Okay, so that's what we have there. Okay, so what are we going to have in that bracket? So it will be 1 over lambda is equals to 1.096 times 10 to the power 7. And then inside here, okay, it will be 1 over 9 minus 1 over 81. Okay, so when you subtract, oh, no. Here it's 6, right? It's 6 squared. So here I'm supposed to get 6 squared. Okay, so this one should be 6 squared. So this one here we have 6 squared. So it means there I'm going to get 36, right? Okay, so it will be 1 over 9 and then minus 1 over 36. Okay, so if you evaluate this, okay, you're going to get 4 over 36. Right, so this is what we are going to have. And then from there, just multiply. Okay, so multiply this part with 4 over what? 36. So you can first divide 4 by 36. Okay, you should get 1.096 times. Okay, so let's divide this first. 4 divided by 36. I'm getting 0.11111, something like that. Okay, so it means here now I can multiply those two. Okay, I can multiply those two. So we're going to say 1 over lambda is equals to this multiplied by this. Okay, so according to my calculator, I'm finding, okay, when I multiply that, I'm finding 1.22 multiplied by 10 to the power 6. Okay, and then here, remember our interest is the lambda. So if you want, you can say this over 1 and then you cross multiply. Okay, but a faster way is just switch this. Okay, take the lambda on top, bring the 1 down. Even here, take the 1 on top, bring this number down. So we're going to have lambda over 1 is equals to 1 over 1.22 times 10 to the power 6. Okay, so now just punch that into the formula, your calculator. So 1 over this, okay, my calculator is giving me what? Right, so when I punch that, my calculator is giving me approximately 8.2 times 10 to the power minus 7 meters. Okay, so make sure you counter check with your own calculator. But here they said the wavelength should be in what? Nanometers. Okay, so we are going to convert this to nanometers. Okay, so how do we convert the meters to nanometers? Okay, remember we said 1 meter is equals to 10 to the power 9 nanometers. So we just use this conversion. So we have 8.2 times 10 to the power minus 7 is equals to x nanometers. So we cross multiply. We see that this and this have the same base, so we can add the powers. So that would be minus 7 plus 9. Okay, so it means x there will just be 8.2 times 10 to the power 2. Okay, so that will mean that we move the decimal place 1, 2. So it means our wavelength in nanometers would just be 820 nanometers. Alright, so we've calculated our wavelength. Okay, so we can keep it so that we can use it to calculate these frequency and the energy and whatever we want to calculate. Okay, so I'll write it here. So I'll say wavelength is 820 nanometers. Okay, or it is 8.2 times 10 to the power minus 7 meters. Okay, so we are going to use it. So we've calculated the wavelength. Okay, let us now calculate the energy. Okay, so we know that the energy is just equals to Planck's constant multiplied by speed of light divided by lambda. Okay, So Planck's constant is this times 10 to the power minus 34. Okay, so this is not the only formula that you can use to calculate energy. Okay, you can use another one. And then the speed of light is 3.0 times 10 to the power 8 divided by, okay, the the wavelength. Okay, so the wavelength that you are going to be using in this formula should be in meters, so we are going to use this one. So 8.2 times 10 to the power minus 7. Okay, so what is left is just to punch the values that you have there into your calculator. So again, isolate the ones that have 10 to the power something. So this one we can write as 6.626 multiplied by 3 divided by 8.2, and then multiplied by 10 to the power minus 34 multiplied by 10 to the power 8 divided by 10 to the power minus 7. Okay, so you can easily divide this on your calculator. Okay, and then this one here, just use the rules for exponents. Okay, all right, so what am I going to get there? Okay, so when I do this on my calculator, I'm getting 2.42 multiplied by 10 to the power minus 19 joules. So this will be my energy. So let's confirm if we are going to get 10 to the power 19. So here we have minus 34 and 8. So we can add those. Okay, so minus 34 plus 8. Okay, I'm going to get 26, which will be a minus. So I'll get 10 to the power minus 26, and then I still have 10 minus 7. And then from there it will be 10 minus 26 minus 7. So it will mean 10 minus 26 plus 7. Okay, so it is minus 26 plus 7. I'm getting 10 to the power minus 19. Okay, and then what about here now? Okay, if I divide 6.626 multiplied by 3, okay, and then I divide it by 2.42. Yeah, so I'm getting 8.2, and then 1, and then 504, something like that. So we round it off to 2 decimal places. Okay, we should get what? Round it off to 2 decimal places. Okay, I think let's do this again. Oh, okay. See where I made the mistake. So here I wrote this number, and then when dividing, I divided with this one instead of this. So it's that number there divided by 8.2. Okay, so I'm getting this same 2.4241. So when we round off these to 3 significant figures, it's this number that we can see here. Okay, so it can also be an easier way to manipulate your multiplications like that. Okay, so just separate the ones with the 10 to the power something together, and then these ones without together. So you can divide this to simply, and then here just use the rules for the exponents. Okay, so this here is the energy that I'm finding. Okay, please counter check with your own calculators. Okay, and then the other thing now is to find the frequency. Okay, so frequency is not hard. We know that the frequency is equals to the speed of light divided by lambda. Okay, from the formula, speed is equals to lambda multiplied by the frequency. So frequency is going to be equals to the speed of light divided by the lambda. So the lambda is this guy. So 8.2 times 10 to the power minus 7. So when I divide this, okay, even here you can do 3.0 divided by this, and then here you just apply the laws of what? Exponentials. Alright, so what I'm going to get there will be, okay, I'm getting 3.66 times 10 to the power 14. Okay, so you can also do it step by step. Let's try. So the purpose I'm telling you this, guys, I don't want you to suffer when dividing these numbers. So we are saying we are dividing this alone without the 10 to the power something. So 3 divided by 8.2, okay, it gives me 0.3. 65853 whatever, and then multiplied by, here I have 10 to the power 8, and then since I'm dividing here, it means I'll subtract, so the power there is minus 7. So what I'm going to have here is 8 plus 7, which will just be what? 15. Okay, so the power there will be to the power 15, and then I want to put this number in scientific form. Okay, remember we said the number that should be here should always be greater than 1 but less than 10. So I have to move this point one place like that. So if I move it, it means it is 3.6. Okay, I can round off this one here because this one is 8 here. So it gives me 6/6 like we have, and then times 10 to the power. Okay, so I've moved to the right like that. So it means from this 15 I subtract a -1, I'm going to get 14. So that's the idea there. Okay, so the units for frequency are just Hz or hertz. If you want, you can write seconds like that, okay, or 1/second. So any of those. Right, so we've found the frequency, the energy, and the wavelength. So the next thing now is to answer B. So B, they are saying what? Okay, so on B they are saying what would be would we be expected to see the light corresponding to this line spectra? Okay, so remember those series that we said? The final one here is what? N3. So what was the series when the n was 3? If I can go back to here. So the series when n is equals to 3, we said they were the what? The pass chain. These ones here. And the pass chain, okay, are related to what? Infrared radiation. Okay, so can you see infrared radiation? The answer is no. You can't see infrared radiation. Okay, so you're going to say no, we can't see it. And then on the explanation, you're going to say when n is equals to 3, it means, okay, it means the radiation is infrared. Okay, and infrared is not visible. Okay, or you can say that, okay, if you don't want to use this, you can say no, and then in your explanation, okay, in your explanation you are going to say that, okay, in your explanation you are going to say that the range, okay, the range of visible light, okay, the range of visible light is from about 400 nanometers, okay, to 700 nanometers. Okay, but when we found the wavelength for this, okay, when we found the wavelength for this, we found it was this, and when we changed it to nanometers, it was 820 nanometers. So 820 is above this range for what? Visible light. So you can only expect it to see light if it's between 400 nanometers and what? 700 nanometers. So if it's above that one, then we can't see it. It won't be visible light. No wonder here we're saying no, okay? Because the wavelength is above the range of visible light. So it's in the infrared region, so we can't see it. So that's what we explain there. Okay, and then we can look at the last question, which is question 4. So question 4, they're saying calculate the energy, okay, and wavelength of light emitted for the electronic transition from infinity to Lyman series. So we said the Lyman series, the n is always 1. So you see that you have to know the series, right? Because sometimes they can just bring a question like this. They won't state the final, they won't state they won't state the final, they'll just tell you the name of the series. So the name of the series is Lyman. So Lyman, we know that n final is 1. And then they're saying from infinity. So it means our n initial will just be what? Infinity. So they want us to calculate the energy, okay, and the wavelength. So we're going to use Rayberg's equation to find the wavelength. So we're going to say 1 over wavelength is equals to, okay, 1.097 times 10 to the power 7, and then we put the transition here, which will just be 1 over n final squared. So n final squared, our n final is 1 because we're dealing with Lyman series. Okay, so I'm going to write 1 squared minus 1 over n initial squared. So any initial is infinity, so I'll put infinity here and then squared. Okay, so infinity is a very big number. Okay, and then you're even squaring it, so you're getting it even a bigger number. Okay, a bigger number. So this infinity, okay, if whenever you have 1 over infinity, this here is the same as 0, or we can say this tends to 0. Why? Because if you're dividing 1 by a very big number, okay, it will be going towards 0. So if, for example, I have 1 over 1, I'm going to get 1. Okay, if I have 1 over 10, I'm going to get 0.1. If I have 1 over 100, I'm going to get 0.01. If I can continue it from here, 1 over 1000, I'm going to have 0.001. Okay, so as we are increasing the number in the denominator, this number tends to go to 0. No wonder we are saying 1 over infinity will just give us what? A 0. Okay, 1 over infinity will just give us a 0. So what we have is 1 over lambda is equals to 1.097 times 10 to the power 7. Okay, and then here 1 over 1 is 1 minus, this becomes 0. Okay, so it's the same as this thing multiplied by 1, which is the same thing. Okay, so we want to find lambda, that's our purpose here, or our wavelength. So we're just going to switch them. Lambda goes up, 1 comes down. This number is the same as divided by 1, so 1 goes up, this number comes down. So what I have is lambda over 1 is equals to 1 over 1.0797 times 10 to the power 7. Okay, and then from here, what are we going to do? Okay, we're just going to divide. So take your calculator and punch in these values. You should get approximately, okay, you should get approximately 9 point, not 9 point, but 91.2, okay, times 10 to the power minus 9, and then meters. So this will be the wavelength in meters. Okay, so remember we said our wavelength should be in what? Nanometers. So we can convert this guy to nanometers. So we use that ratio. We said 1 meter is equals to 10 to the power 10 to the power 9 9. I think this one is not correct. Okay, so let me punch this again into my calculator. I'm getting confused. Okay, let's punch it again. So I have 1 divided by, okay, and then I have 1.097 multiplied by 10, okay, to the power 7. Okay, I'm getting 9 point. All right, I'm correct. So this is the value of the lambda. Okay, I thought my calculator was wrong. And then now we want to convert it into the nanometers. So we know that 1 meter is equals to 10 to the power 9 nanometers. So if I have 91.2, I mean, okay. So this is 91.2 times 10 to the power minus 9 meters. How many nanometers am I going to have? So they are just cross multiply. X will be equals to, so this here is multiplying this, and then they have same powers but different signs, so that will just be 10 to the power 0, which is the same as 1. So it means our wavelength in nanometers will just be 91.2 nanometers. Okay, so I'm going to say lambda is equals to 91.2 nanometers. Alright, so after we calculate the lambda, we can now calculate the energy. Okay, so the energy, we use this formula. Okay, so that's the formula that we're going to use. So let's use, because now we have the lambda of the wavelength. But remember the wavelength that we're going to put in this formula, it will be this one here in meters and not this one here in nanometers. This one, we just found it to satisfy what they wanted there. Okay, but when calculating energy, we use this one in meters. Okay, so we're going to say energy is equals to, okay, Planck's constant 6.626 times 10 to the power minus 34 multiplied by the speed of light divided by the lambda, which is 91.2 times 10 to the power minus 9. Okay, so again here just separate whatever does not have 10 to the power something, separate it. So what we have is 6.626 times 3 divided by 91.2, and then whatever has 10 to the power something, 10 to the power minus 34 times 10 to the power 8 divided by 10 to the power minus 9. Okay, so there you can evaluate this. Okay, so the answer that you should get there should be 2.18 times 10 to the power minus 18. Okay, so this is the answer that I'm getting, and these are joules. The energy is joules. Okay, so we've calculated the energy and the wavelength. All right, so that's basically it for today. Okay, please try out these questions. Okay, feel free to try out these questions on your own. Okay, and if you need help in your NS, okay, it can be any subject: math, chemistry, physics, biology. Okay, feel free to contact us. Okay, or you can register on our website in the comment section below there. Okay, so thank you so much for watching and have a blessed night.